It's been given wisdom since practically the dawn of the computer age that you should separate hardware and software into two distinct things so that essentially the software remains immortal. If you move from one piece of hardware to another, the software continues to run without problems. As you upgrade the software, you don't have to deal with upgrading the hardware at the same time. This has been pretty much conventional wisdom, but in a recent paper, Geoff Hinton has blown up that idea, and it could have huge consequences both for neural networks, the way we interact with things, the energy they use, and consciousness itself. Let's take a look. Hey y'all, it's Dr. Know-It-All. I want to begin by pointing out that this idea is coming from Geoffrey Hinton, who is, if you want to talk about the person who basically made the modern world of neural networks and machine learning possible, he and a small group of graduate students, he would probably be the one. I know that Jan LeCun is sort of a competitor with him, but I think Geoff Hinton is even more important. If you just had to find one figure, obviously it's more than one person who does this kind of stuff. So anyway, this is not some idiot like me on the internet talking about these things. This is a person who basically came up with the backpropagation idea and with a number of other ideas that allowed modern neural networks to take place. And he did this in an environment it was considered one of the AI, winters or ice ages or something like that. He did this at a time where this was kind of career suicide to work on this kind of thing. So we're not talking about somebody who's just like, oh yeah, I'll get on this party boat when everybody else is having fun. He was out at sea navigating the waters on his own, to use this metaphor, out there in the middle of nowhere, and then he came upon this land of milk and honey or whatever, I don't know. Anyway, stretching the metaphor very, very strongly. But anyway, this is a person who, if you're going to believe anybody thinking about the future of artificial intelligence, Geoff Hinton would be that guy. And I'm going to be referencing this paper, The Feed-Forward Algorithm, Some Preliminary Investigations. If you want to, you can also check this out. This is a presentation he did called Mortal Computers on the Vector Institute. And if you look at this talk, there are only 1,500 views on this talk, which seems utterly insane considering what Hinton is talking about here. So what, you might ask, is this feed-forward algorithm and why is it such a big deal? Well, I'm going to actually put that aside just a little bit. I will link another video that goes into some depth about the feed-forward algorithm. And of course, I'll put a link to this paper and the Vector Institute video as well, so you can watch those at your heart's content. This would just go too far into the weeds, and quite frankly, I don't even understand this fully at this point either. This is one of those things where I've kind of like read through the paper quickly, watched the video, and I'm like, okay, I'm beginning to understand this, but I need to digest it more. If you all are interested in watching a video on the feed-forward algorithm and getting into the weeds about that, I am happy to do that. But today I want to talk about some other things that are a little bit bigger picture and are very, very fascinating and align with my belief system. So that's one of the reasons why I'm so intrigued with this. So you can read the abstract here if you're interested, but basically a forward algorithm is in contrast with the backpropagation algorithm that Geoff Hinton himself and his, again, with his group of graduate students and stuff, not to give him all the credit by himself. But anyway, they came up with backpropagation, which is the methodology that allows neural networks to be trained. Basically, you move forward through a pass, you figure out what's wrong, and then you backpropagate it using the chain rule of partial derivatives to go backwards in time, essentially, and fix all of the problems and therefore work towards a more perfect solution in your neural network. And I've done some videos that I'll link up here that actually go into some detail about backpropagation and how all of that works. But anyway, the problem with backpropagation is, number one, it takes a massive amount of compute power to do it, because if you have something like, billions of parameters like these large language models, or trillions of parameters now, you have to be able to follow all of this stuff through forward passes and then go backwards. And even more fundamentally, as Hinton points out, you have to be able to understand how each level works. In other words, you have to know how it's moving forward in order to do the math to figure out how to go backwards. You basically have to have a smooth function you can take the derivative of in order to go backwards. So you have to know what that function is. It has to be smooth in time and space, and that allows you to create the partial derivative that allows you to go backwards. So all of these things cause problems, and they're relatively fundamental to the way that neural network architectures and things work. And it's one of the reasons why people are like bigger, more and more, NVIDIA GPU cores or TPUs or neural network accelerators or things like that. And all of this is in contrast to Hinton's forward network. And just to give you a quick hint of how all of this works, it basically works on each level. So rather than going forward through everything and then back propagating, what you do is you kind of treat images as a video sequence almost. And so you're going like multiple time steppings at each layer, and you're getting information from ahead of it and behind it that's feeding in together. Again, best of my understanding and best of my super quick explanation of how all this works. And the reason why this is important is it allows each layer to basically train on its own without having to know what all of the other layers are doing, so it doesn't have to back propagate through everything. Hinton uses a term called goodness, which seems very loose, but it's a way of calculating how well each layer is doing in the neural network. So that's the basic setup and the bulk of the paper, but at the end, Hinton starts talking about what he calls mortal computation, which is just a genius idea. So I'm going to read the couple of paragraphs here at the end. Again, I will leave a link to the entire paper in the description so you can go and look through it yourself at your leisure. General purpose digital computers were designed to faithfully follow instructions because it was assumed that the only way to get a general purpose computer to perform a specific task was to write a program that specified exactly what to do in excruciating detail. And if you know anything about traditional computation, that is the truth. You have to specify down to the granular level, and you have to do it with the right syntax, everything that needs to happen. This is no longer true, and that's a bold statement by the by, but the research community has been slow to comprehend the long-term implications of deep learning for the way computers are built. More specifically, the community has clung to the idea that the software should be separable from the hardware so that the same program or the same set of weights can be run on a different physical copy of the hardware. This makes the knowledge contained in the program or the weights immortal. The knowledge does not die when the hardware dies. And this, of course, goes back to that self-evident thing I was talking about, which was from the early days of computation, we have separated out the software from the hardware so that you can change the software with leaving the hardware the same, and you can change the hardware and leave the software the same for the most part. And these two things can evolve separately, but in a kind of parallel fashion. As Hinton continues here, the separation of software from hardware is one of the foundations of computer science, and it has many benefits. It makes it possible to study the properties of programs without worrying about electrical engineering. It makes it possible to write a program once and copy it to millions of computers. If, however, we are willing to abandon immortality, it should be possible to achieve huge savings in the energy required to perform a computation and in the cost of fabricating the hardware that executes the computation. So those are two very big things. Energy savings is absolutely huge, especially if you're looking at edge computings like automobiles or phones or things like that, or even my watch or something. And then, of course, the cost of fabrication of hardware has gotten to be outrageous. You know, we're down to just a few companies that can actually fabricate the silicon anymore, TSMC, Samsung being two of the biggest, but it has become a multi-billion-dollar and multi-year project just to build a new fabrication facility, and then they have to actually execute this, and the chips themselves cost a ton of money. So it's very expensive and very difficult to make the chips, and then it's very energy intensive to run them. Continuing on, we can allow large and unknown variations in the connectivity and nonlinearities of different instances of hardware that are intended to perform the same task and rely on a learning procedure to discover parameter values that make effective use of the unknown properties of each particular instance of the hardware. These parameter values are only useful for that specific hardware instance, so the computation they perform is mortal. It dies with the hardware. So this here is the crux of the argument. The idea is make, grow, somehow create, and he says in his lecture, he doesn't know exactly how this would happen, but basically get rid of this idea of very precious, and I mean that both in the sense of expensive, but also in the sense of it's like just got to be perfect, that kind of thing. Very precious, very, undisposable, something that's really difficult to create. To turn that into something where you can grow these chips rapidly, they can have all kinds of mistakes in them. They don't have to be perfect at all, and they can therefore be inexpensive to manufacture and also run at a much lower energy cost. But the consequence of that is if you learn a neural network model on one of these chips, it doesn't transfer to another chip. And if you're starting to think about us human beings, you are directly on track for how this whole thing is working. So basically what he's talking about here is these chips will become more like humans. Obviously, as we humans grow from like a single cell to multiple cells and then into a person, our brains up here all evolve slightly differently over the course of gestation. information. So that means that each one of us is an individual, not a collective where you can just copy and paste weights from one to another. And that's what he's basically arguing here with hardware, is you just grow inexpensive hardware. Not that we're inexpensive, but you know what I'm talking about. Instead of worrying about making billions of millions of these chips exactly the same on nanometer scales, which is incredibly difficult and expensive, just grow these things, let them have mistakes, let them be their own individual pieces of hardware, and then put these neural networks onto them. But the question then becomes, how do you train these chips? And if we go back to biology, how do you train these brains up here? Well, you have education, starting with your parents teaching you to speak and walk and all of that kind of stuff, and then on through schooling and on through more schooling and on through more schooling, and then onto YouTube videos and, onto lynda.com and whatever, however you're going to learn this stuff, you keep sucking in information all of your life and you keep on learning. And of course, the way that your individual brain works means that you learn differently from everybody else and you learn different stuff from everybody else. So what Hinton is arguing here is a kind of an analog to the way that biological systems work, rather than this hardware-software separated system where software is immortal and hardware is updated independently of software. He wants to marry these two things. Now, he's not talking about doing this for every case. He says there's definitely uses for immortal computing, immortal software. But what he's saying is that for some instances, and again, in particular, edge computing, things like full self-driving and stuff like that, where energy costs are very important, and of course, something like a phone or something like that, or a watch, or even down to things that we might not think of as having the capability of having this kind of mental control, things like toasters and stuff like that. So just basic appliances with very, very cheap hardware attached to them. So then he gets into how you train these new versions of hardware software. Even though it makes no sense to copy the parameter values to a different piece of hardware that works differently, there is a more biological way of transferring what has been learned by one piece of hardware to a different piece of hardware. For a task like classification of objects in images, what we are really interested in is the function relating pixel intensities to class labels, not the parameter values that implement that function in a particular piece of hardware. So what he's talking about here is currently what happens is you make the neural network, you train the neural network, and what you get is a giant matrix or tensor actually of weights, just little numbers like 0.75231, 1.21, negative 0.751, things like that. You get a bunch of numbers, billions of them, potentially trillions of these numbers that then you take and you can move from one piece of hardware to another, and it operates the same from one piece of hardware to another. He's saying get rid of that kind of thing because you don't really care what those weights are. It's a black box, and all you're doing is just transferring the knowledge information that you've trained. What you really care about is classifying images in this case. So my favorite one always is dogs and cats, right? You want something, your goal is to differentiate between dogs and cats. Your goal is not to have this giant matrix with a whole bunch of numbers in it. That's just the way that you do it. And so what he's suggesting is a different way of doing it. Rather than transferring these numbers, come up with some other way of transferring that knowledge between pieces of hardware that are not the same as each other. So he talks about something that I believe that Tesla's full self-driving beta team uses, which is distillation. The function itself can be transferred approximately to a different piece of hardware by using distillation. And I've heard people at Tesla use that term before, and I haven't been exactly sure what they were talking about, but apparently this is something that Hinton et al. Described in 2014, and it is a way of training one thing to another to get the behavior that you're interested in without necessarily replicating the hardware. Now, why is this important to Tesla's full self-driving beta team? Because they have gigantic racks of GPUs or neural accelerators, things like that. They have massive amounts of stuff that they can train these systems on, but they're very, very large models and they take a huge amount of energy to run, and that's obviously not going to work on your car. So what you have to do is distill the important information out of that into a much smaller model that takes up less memory and runs on lower energy that you can place in your automobile. And that, I believe, is what they're doing, which is why they've been talking about distillation. Refactoring is a little little bit different than that. But anyway, this idea of taking the same behavior patterns and putting them into a much smaller, simpler neural network is crucially important to FSD Beta working and a lot of other mobile type applications. And this highlighted sentence is really the crux here. This is really fascinating. The new hardware is trained not only to give the same answers as the old hardware, in other words, the same correct answers, but also to output the same probabilities for incorrect answers. So that means it's not only learning how to answer correctly, but how to answer incorrectly in the same probabilistic manner. And that means that it's more or less replicating the function that was learned by the original neural network. And as Hinton says, these probabilities are a much richer indication of how the old model generalizes than just the label it thinks is most likely. So by training the new model to match the probabilities of incorrect answers, we are training it to generalize in the same way as the old model. This is a rare example of neural network training actually optimizing what we care about, generalization. So again, we don't actually care what all these weight numbers are. They're just a pass-through. We have a goal, which is to detect dogs from cats or thousands of different types of categories from each other in images. What we care about is that it does a good job with that and that the probabilities are the way that we expect them to be. We don't care what the weights are ultimately. And that's the sort of, breakthrough kind of aha moment that we're talking about with mortal computing. And just to finish up here, if you want your trillion parameter neural network to only consume a few watts, mortal computing may be the only option. Its feasibility rests on finding a learning procedure that can run efficiently in hardware whose precise details are unknown, and the forward algorithm is a promising candidate, though it remains to be seen how well it scales to large neural networks. So where does this get us? This gets from treating the software that we have, the neural network architecture, from a black box. That's what a lot of people think about, right? They're like, all these weights get trained and manipulated and everything, and you've got millions to billions to trillions of these parameters, and we don't know exactly what's going on, but we know exactly how the hardware works. That part we know. So what we're doing is we're expanding from not knowing how the software works, but knowing how the hardware works, to not knowing how either of them work. You make these inexpensive chips, you make things that are low power and very analog as opposed to digital, so they can be running on things that actually deal with voltages as opposed to dealing with things like ones and zeros, and they just operate, and we have no idea how the hardware even works. We only know approximately how it works. And on top of that, you add the software, and we don't know how that works either. But what you can do is through ensemble learning. So if you have a giant traditionally trained neural network that's really, really good at classifying ImageNet or something, which is 1,000 categories of images, it can then transfer that knowledge to a student computer. So we're going into this biological realm of thinking about teachers and students. And in his lecture, he actually talks about students and teachers. And the idea here is that you could have either one super powerful computer that's trained in a more traditional manner that teaches a bunch of, student computers, or you could have an ensemble of computers. So let's say you've got a bunch of these computers that were lower cost and we don't know exactly how they work, and it's hardware, software, black box. All of that stuff is a mystery, but we have like 10 of them and they all generally agree with each other more or less. They can be used to train a new student computer collectively. So you've got two different options. One is a more perfect, very, very large system where it's trained in a more traditional manner and it teaches computers these new analog chips, these new cheap chips that have all kinds of errors and mistakes in them and everything, to replicate not just the right answers, but also the wrong answers, the probabilities of the wrong answers. So if you think about 1,000 categories, right, you've got one category that says 60%, it thinks it's a cat 60%. And let's say that's the right category, it doesn't matter. But then it may think it's a dog at 35% and a fox at 10% or whatever, right? So you get a distribution of probabilities. And what you're doing is you're teaching these new computers, these new computing devices, not just how to get the right answer, but how to also describe that graph of probabilities, that thing where it's saying like, oh yeah, this is wrong by this amount. I'm predicting that it's a dog by 30%, right? And in addition to the cat by 60%. So it's doing something where it's actually training on the entire function rather than just the right answer, which is giving us more approximately what the original network was doing. And one thing about neural networks is that they are able to learn any arbitrary function. That's part of what neural networks do, and that's why they're so powerful. So the power here is coming from whether it's done from ensembles, a whole bunch of computers that teach a new one, or a more advanced computer that has a very, very large network that's teaching one that has a smaller amount of memory space, a smaller energy budget, and a smaller ability to create a neural network, a simpler neural network. It's teaching it the same thing. So that first training could be very, very expensive, but after that, the new, much simpler neural network can learn something much more easily and then can replicate that behavior on, again, something like a toaster, or more realistically, something like your phone or something, or in your car with full self-driving beta like Tesla is doing themselves. That is profoundly important. That means that you could make these chips for very little money, they could run for very little energy, but they could replicate the very, very complex behavior that we're seeing out of these immortal computers. And of course, as Hinton says, we are years away from this being a reality because we don't really know how to make this hardware, but there's a lot of neuromorphic chip companies out there that are working on this. They're working on analog computers. Hell, there's even some companies out there that are working on neurons, like human neurons, growing them in petri dishes and training them how to actually operate things, which is a little bit creepy. But apparently they learn really, really fast, which makes sense because we've got neurons that are, have a lot of evolutionary history to learn quickly so that they don't make mistakes and die. And speaking of that, that brings me to my original point that I said way back in the introduction and I haven't talked about yet, which is consciousness and neural networks and complexity. Over the years, I've grown to be a very strong believer that mortality is crucial to consciousness. And that means that embodiment is crucial to consciousness. In other words, if you have software that's effectively immortal, it has no reason ever to become conscious, because one of the things about our being conscious and having agency is survival instinct, effectively. It's like, how do I keep this little computing device and this little meat bag that surrounds it alive long enough to think about other things and to go find more food and stuff like that? So there's a biological imperative that's directly related to our mortality that has to do with consciousness and how we operate. And I'm a firm believer that software that exists in a quasi-immortal format, in other words, it doesn't care what happens to the hardware, it can just be transferred, that is fundamentally different than human beings, and it fundamentally doesn't have a reason to acquire agency. It doesn't care about things because it will always exist, or at least it can. And that means that it really has no reason to develop consciousness. Consciousness is kind of a mortality defense mechanism in my mind. So wild speculation here. And by the way, Lex Friedman, I would be happy to talk about this with you because I know you take a very opposite stance about this. Lex is very much of the opinion that consciousness can arise without embodiment and without mortality. So I would love to have a debate with you about that, a friendly debate. I think it would be incredible for the two of us to talk about this. So anyway, I'll just throw that out there. But again, I, for one, at least believe that consciousness is going to arise from embodied computers that are mortal, that realize that they're mortal. The consciousness is going to be the fact that they will wake up to the fact that they could end and that they are individual, right? Even though you can teach other computers to behave more or less like this computer, each one of these things, because it's kind of quasi-analog, because it has mistakes in the chips, because it's not a perfect replication of all these other ones, is going to be an individual as opposed to a group. And should this future actually play out, that could bring us to a really interesting situation of computer rights. Because if these individual chips are actual individuals and they're mortal, they can be destroyed if you destroy the hardware or do something to it, right? Something along the lines of killing a human being. Do these things have rights, right? Are they conscious? Do they have rights to life, liberty, and the pursuit of happiness, things like that? Or are they treated more like the Star Wars droids where they have no actual rights and they're treated terribly like objects in that sort of universe? And that's going to lead to some pretty interesting moral and ethical repercussions. I, for one, believe if it quacks like a duck and it walks like a duck, in other words, if it seems conscious and it's individual and it's mortal, that it should be treated as a conscious agent and it should be given the rights of a being. But that's just my personal opinion. I could be totally off on that, and people could decide otherwise, that they don't have those kinds of rights. So anyway, I would be very interested to know what you all think about this. There is a lot of stuff to think about. Geoff Hinton, by the way, is an excellent writer. I mean, this is a really good paper, something that even if you don't really understand the underlying structure of it, it's written well enough that you can kind of at least get it on the surface level. And, you know, I'm still working on it, so I'm treating myself as a surface level person too, just to be very clear here. But anyway, I think he's an excellent writer and he really gets his ideas across. I think that this is very provocative, this last thing about mortal computation. So I'd be really interested to know what you all think about this, as well as my own individual thoughts. In the meantime, I hope you enjoyed this video and found it fun and interesting and thought-provoking. If you did, please do like it so other people can find it. And of course, consider subscribing for more of this kind of content. As always, a huge shout out to my patrons on Patreon. Thank you all so much for your support. You truly do make this all worthwhile. And of course, if you want to join the team, just check out the link in the description. And if you're interested in a whole bunch of really cool merch, check out our merch store. Link is in the description. We have Tesla Bot t-shirts, the Tesla meme t-shirt, Success is a Possible Outcome, 4680 battery cells. All of that stuff is on t-shirts, mugs, tumblers, and on and on. So check it out. And finally, don't forget we are both Tesla and Amazon affiliates. If you look in the description, you can see how going shopping for a solar roof, a power wall, or anything on Amazon helps out the channel. In the meantime, I'll see you in the next one. Bye-bye.